ATI Firth Sterling is a tungsten carbide parts manufacturer in Houston, Texas. Facility management has identified the sintering furnace process as a manufacturing bottleneck, limiting production capacity. The following need statement was developed for this project. Identify and analyze methods to increase the production capacity of a pressurized sintering furnace by decreasing the cooling time of the heat treatment cycle through cost-effective modifications to the furnace cooling system without compromising part quality. The parts are inserted into the innermost region of the furnace, inside a graphite radiation shield known as the coffin. This coffin is placed inside the region known as the inner chamber. The inner chamber contains the heating elements, and during the heating process, temperatures in this region reach upwards of 1400 degrees Celsius. The inner chamber is separated from the outer chamber by a foam insulation package. This insulation is very effective at restricting heat flow and proves to be a major obstacle during the cooling process. The outer chamber is enveloped by a stainless steel vessel wall. The furnace manufacturer has imposed a constraint that the vessel wall temperature must not exceed 200 degrees Fahrenheit. The vessel wall is cooled by a water jacket that flows around the outside of the pressure vessel. This plot illustrates the inner chamber temperature response over the course of the current cooling cycle. As you can see, the temperature decreases much more rapidly after the inner door is opened. This is due to the increased heat exposure to the vessel wall and water jacket. In order to perform a comprehensive heat transfer analysis of the furnace system, a thermal model was constructed in MATLAB's SimScape software. By developing a thermal resistance network for the heat transfer from the parts all the way through the cooling system, concepts could be virtually tested and evaluated to estimate their effects on cooling performance. After extensive modeling and financial calculations, the following solutions have been selected by the design team. Substantial cooling time reduction can be achieved by inducing airflow inside of the furnace, as this increases the convective heat transfer. The team suggests that a system be installed to recapture the argon that is currently vented into the atmosphere by implementing a system such as the one shown in this figure. Additional improvement can be made by replacing the current external water-to-water heat exchanger with a filter. This would allow for colder furnace inlet flows while still preventing contaminants from damaging the water jacket system. Cooling time can also be decreased by installing a chiller system on the plant water line. This would increase the temperature gradient between the hot parts and the cooling water, thus increasing heat transfer rate. Additional time savings can be realized by simply opening the furnace door and removing the parts at a slightly higher temperature. By combining these modifications, the cooling cycle can be potentially reduced from 12 hours to 8 hours. The implementation cost is estimated at $493,000, with a payback period of approximately 3 months. This improvement allows for a 34% increase in production capacity, valued at approximately $2.2 million per year. In conclusion, calculations show that ATI Firth Sterling has potential for significant production capacity increase with relatively minor system modifications. The design team strongly recommends that ATI invest more time into the pursuit of these solutions.